I guess today is more about just a very light touch introduction to some aspects of deep learning and how maybe my own research or other research has contributed to that field, especially for medical imaging applications. So today I would say that I'm going to touch upon 3 case studies. 2 of them relate to my previous work, and one is a bit more generic one from other researchers. But I thought that before that, given that the audience that we are here now, it's not necessarily experts on the machine learning side or the deep learning side. We have a mixed audience. I thought that initially it would be a bit more appropriate to start with a soft introduction to some concepts about deep learning, and then as we move along, we will see the 3 case studies, and I guess that is a point where we can engage in discussion about aspects about the findings or how we went about doing that research and what type of implications that might have in the future. So I think Neil said some things about me. Previously, I was with the University of Lincoln for a few years, and then before that, I did a stint in industry in Germany. I stayed for a year working on machine learning again for medical applications, and even before that, I was at Cardiff University. So I have worked with different stakeholders and different applications in the last decade. I would say, as it currently stands, I'm not really involved in any medical imaging project because I stopped actually working with medical images a couple of years ago, and I will maybe elaborate more on that as we approach the end of this presentation. Maybe I can give some reasons why maybe I haven't continued working on that area and why I am interested in exploring this area again. So my main, let's say, my initial involvement with medical images started, I think, quite a few years now, when I first did my MSc thesis, and my MSc thesis was on machine learning for diabetic retinopathy detection. And to do that, we use, of course, retinal images. And then I went on to continue in that field for a few years. I even did a Marie Curie fellowship on that domain. But then I kind of decided to change a bit the focus area, and I investigated other type of applications like energy. I worked a lot with Siemens gas turbines and nuclear reactors across some European projects that we had, and then I have some UKRI projects on environmental data, and of course, in all of that aspect and all of that umbrella, I would say that computer vision has been my main focus, and at least from my perspective, although you will see that in practice, medical imaging and computer vision are kind of considered to be separate domains when we speak broadly in our community, but you could even consider that medical imaging is a subfield of computer vision because we still have images that we usually utilize when we develop different approaches. As I said, I prefer to start softly with some sort of background on machine learning, and then why we have now deep learning being one of the main technologies that are being used in medical imaging, and then we can see together some examples for medical imaging and potentially as well discuss about the difference between the pre-deep learning era when we had handcrafted features, and then in the last decade when we have this surge of deep learning research, and then we have this automated feature extraction for segmentation or detection of a disease and so on. So machine learning, I guess you are more of you are familiar with this area. You've heard something, or maybe you are interested in that area. I would say that, broadly speaking, a consensus about machine learning definition, because you will find different types of definitions focusing on different aspects of machine learning. But I would say that from my perspective, machine learning, we can consider being an intelligent system that takes some input data, learns some sort of high-level information, patterns in the data, so that we then are able to predict something. And of course, that is not a kind of a pipeline that doesn't have other components, because machine learning can be combined with other approaches. For instance, you might have different types of AI approaches, like ontologies or knowledge graphs, and then basically you can combine data-driven models and machine learning with knowledge graphs and ontologies or other type of neurosymbolic approaches, so that you then have a blended approach. Okay, but of course that is a more, let's say, philosophical discussion, because it depends on the problem definition, it depends on the type of data that we have, depends on the amount of data that we have, and then you decide which technique might be more, let's say, suitable for the problem that one tries to solve. I think one of the main advantages, I would say, for machine learning, and I think it becomes quite apparent when we deal with healthcare data, is the fact that you can easily, or let's say easier than other approaches, to kind of include multiple data sources for the same problem. For instance, you might have a multimodal approach whereby you combine images, or you might have like numerical data, like tabular data, or time series, and then you can create a hybrid system that extracts information from different data sources for the same problem. So to predict something or to detect something. So you don't have only to think that, if we are using medical images, then we cannot use other type of data that might describe or give additional information for the problem that we're trying to solve. Okay, so that is one of. Of course, when we speak about deep learning, then it's a bit more abstract definition, and now it has become basically, it's still a buzzword, but it's maybe a bit more uncommon if you are focused on technical aspects of deep learning anymore to use that terminology, because deep learning anymore has so many facets. Like there are specific deep learning approaches. So I mean, I would say the last couple of years we mostly focus on specifying what we mean by deep learning. So we will use specific terms for convolutional neural networks, so it's different types of machine learning models within the umbrella of deep learning. So yeah, so deep learning has become a bit more terminology that is not used anymore very much within the technical community. You will still find it when we describe applications, when we speak about the broader understanding of AI, but don't consider that to be uncommon if you find studies that they don't use deep learning as the title, let's say, anymore, because it's not anymore as a popular domain in terms of title, let's say, if I can put it like that. Of course, what you see here is a very kind of simplistic artificial neural network, which is the cornerstone of deep learning models. You see different colors. On the left-hand side, you see this green, the first set of neurons, which is the input layer. So you can consider that this is the point where the network, so the neural network in this case, receives any sort of data we have. And don't think that because you see a nice circle, green colored circle, that means that the data have to be structured in the way you see it here. This is more like a schematic that gives you a high-level understanding that in the input layer you can have images, you can have time series, you can have numerical data, any sort of data that you want to incorporate into the network, right? So the learning process, so what the network learns as part of this exercise, happens in the orange part, so the middle part of the network. So that is the part of the network where all of these abstractions and high-level features and hierarchical structures happen, so that we learn the task that we have at hand. And that means that, for instance, if we have a medical image, right, as an input to this model, or millions of medical images, that is the point where the network will try to identify what are the patterns that might differentiate, let's say, a disease from a non-disease image, right? And of course, that happens in conjunction with the output layer. In this case, the output layer here is the one in blue color. So the magic happens because we have information about what corresponds to a disease or no disease. So we know, for instance, that if we have 1 million images, medical images, then we know that, let's say, half of them show a disease and half of them don't show a disease. So that is one of the fundamental aspects of how a neural network learns. And in our domain, we call that supervised learning, because we have a supervisor in this case, which means a system that tells you, okay, you know what, this image has a disease inside, and this image doesn't show a disease. So it's a normal, healthy subject appearing in this image. And that is the information where the network uses to understand, okay, you know what, what's the difference between healthy and unhealthy images? And that is the process that allows all the learning, phase to complete. Of course, there is not only one way to do that. There are multiple iterations. The network has to be optimized, hyperparameterized. So I present it here in a very simplistic manner, but trust me, when we put the computational demands to train such networks, then we will see that it can, go at a very complex level. And then it's up to us to decide where we draw the line. So sometimes, computational demands might be so high that then we have to consider simpler models, for instance. But that depends a lot on the application that we try to focus on, right? So I think that is, again, another very simplistic example, just to show you, because all of these examples, so the one hidden layer, 1 neuron, one hidden layer, 2 neurons, and one hidden layer, 3 neurons, for instance, it's a very, 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 very simple model still, all of these models. But you can quickly see from these visualizations that even a very simple model with one hidden layer and 3 neurons can still learn nonlinear functions. And imagine now that when we speak about millions of different data points or multimodal processing, that we have multiple data inputs, that is a very high dimensional space, and then we need something more complex to learn all of these interactions that happen at a higher dimensional space. Okay, and that is an illustration of how quickly a neural network can learn some, of course, simple nonlinear functions, but then you can extrapolate that the more complex problem we have, the more complex network we need to get a good output at the end. Okay, so that is a very common pipeline that we see in deep neural networks, right? So I guess in every model, even if we speak about a logistic regression model or generalized linear model, any type of modeling process you want to think about, we always have the training phase where we have, let's say, a training data set that the model tries to learn all of these patterns that we have inside. And then when we have a trained model, so when we have learned all of this information that is, inside this high dimensional space that we are using as an input, then we go to the inference phase. So the inference phase, for instance, could be, in our example, in the medical imaging example, could be that we have, let's say, retinal images from diabetic retinopathy patients. We have, let's say, 1 million of them, and then we learn a model, and then we deploy a model, let's say, in NHS, right? So we have a model that sits in the central computing facilities, and then when we have a new patient that you scan the retina because they have diabetic retinopathy, then you can have the system that will, give an indication of whether this image that you have just captured, whether it is healthy or whether it has macroaneurysms or, at which stage of retinopathy this image comes from. So that is the inference phase, right? So we have to differentiate between training phase and inference phase. Usually, the most computationally demanding phase is a training phase, because this is the point where you might have to go through multiple iterations and many experimentations to find an optimum model, right? So at this phase, we incorporate also the validation phase, right? So we train a model, and then we have, let's say, a different set, which we call validation set, to validate that what the model learns is actually something robust that can be used in real life, like in a deployment phase. So now you will ask me, and that is one of the most common questions I'm asked, when I introduce deep learning to people, is how deep learning compares with other machine learning approaches, and sometimes then the discussion usually goes on to the fact that why do you use deep learning? Is it the optimum way? Is it the correct way? Is it the only way? So these are valid questions, but the point is we have to consider that in my opinion, that's my personal opinion as a data scientist and machine learning expert, is the fact that you always have to think, what the problem is. So you cannot think about a technique before you have a clear definition of the problem that you try to solve. So not every problem needs, let's say, if I can put it like that, a deep learning approach, right? So we have to think what the requirements and assumptions of the problem we have at hand, so that we can design an appropriate experiment, and then deep learning might be a component of the intelligence system that we will employ to solve the problem, right, or to approximate a solution to a problem. Usually, there is the consensus that based on empirical experimentation. We will say that deep learning up to a level, we see a clear improvement in performance with more available data. So the more data we have, the better performance we usually get. Of course, there's always the plateau. So there's always a point where the models start overfitting, which in this case, overfitting means that we start learning noise in the data. So there's no actual improvement. But comparing deep learning with other traditional methods, we see that it plateaus much later than other learning algorithms, right? And that is kind of an illustration of how you can consider deep neural networks, which is pretty much deep learning approaches, how they compare with other more, let's say, popular, or let's say more established approaches that have been in existence for the last 20, 30 years, right? So you see that the accuracy comes at a cost, and the cost usually is interpretability, and that maybe is one of the areas that your questions might focus on later from some of you, how transparent deep neural networks are, and that is a discussion that I'm going to go on to in a couple of slides. So that is more just an illustration of some different deep neural networks that are in existence and are used in practice. So the most common one, the most popular one, maybe the one that is mostly used in the medical imaging domain is the first one that you see, the convolutional neural network, which is a type of neural network, but is more powerful when it comes to extracting information from images. So you see you have an image as an input, and then you have the component that extracts features from the images that you have, multiple images, and then you go on to the an interface like the one I showed you before, when you extract all of these features so that you get an output. In this case, an output could be that the image is a good quality or a bad quality image. So you have an automated system that detects bad versus good quality images, right? And that has been one of the I recall that it was quite common in the past, maybe 2005, 2006. There were some studies quite popular on detecting quality, bad quality images from retinal imaging screening services. So sometimes, for those of you that you might have worked with retinal images before, you see that, especially in the past, maybe early 2000s, some of the capture images were a bit blurry, not of good quality, which means that then the ophthalmologist or the retinal screeners were not able to screen and label the images for screening purposes. So there were algorithms developed for automatically detecting good versus bad quality images, right? So the other model that you see on the bottom, which is called autoencoder, this is another type of model that is used sometimes for unsupervised learning. So in this case, we don't have labels. So in your example, in a medical imaging example, it could be that we have, let's say, 5 million MRI images, and for whatever reason, we do not know whether they come from healthy subjects or from subjects that suffer from a disease or so on. So that type of network tries to extract information from generic images without concern with whether these images have a disease or not. So they learn information that is more, let's say, generalizable, that we can use it in the future with, let's say, with another type of model like convolutional neural networks to, let's say, fine-tune, so to optimize the network. And I will explain that a bit further when we have the specific examples to talk about. Another popular neural net is the generative adversarial network, or otherwise maybe known as GAN, GANs. So that is, you might have seen some examples of this type of network, for instance, from fake celebrity images or fake art. So how you can create art with AI. So let's say this is the family of techniques that are used to achieve that. And that is kind of an approach where you have two different types of neural networks working in parallel and competing with each other, so that, you know, one tries to generate images, that tries to discriminate between the fake and the real images, and then that type of game that they play improves you know, the performance of the generator, so the network that generates fake images, and then this process allows for the technique to generate realistic images, right? Ideally, of course, not everything is as kind of straightforward as I might be describing now. There are many difficulties when it comes to training such models, but I think the high-level idea of what is the purpose of these models, I think, is clear now. The one that we see at the bottom is another type of neural network where we usually use it for time series. So when we have this time component in our data, for instance, we might have you know, sensor data from EEGs, or you know, could be for any type of sensor network, when we have data coming at specific intervals, and then we try to use this time series for either generating data, or we can even detect something, predict something, or, you know, for instance, you might have a network where it takes time series and gives you a diagnosis, right? So, you know, disease or no disease. But sometimes you might use this type of network for, let's say, a regression problem. So you might be predicting a continuous value of something, right? As you would do with a linear, you know, model, like a linear regression model. So it can be used as well, not for detecting the disease, but as well, you know, getting the continuous output for whatever is that we try to predict. This is another a bit more recent type of neural network, which is quite similar to the convolutional neural network. So it works with images. The difference with the convolutional neural network in terms of performance, it comes to the fact that this type of networks are a bit more robust when it comes to different kind of transformations that we have within an image. For instance, if you have some lesions in retinal images, then sometimes, you know, the capturing phase might mean that the landmarks in the image, for instance, optic disc that you have in the retinal images, might not be aligned properly. So you might have the same lesion appearing from different viewpoints. So that type of models have been shown to be a bit more robust when it comes to such you know, novel viewpoints that we can have in real life images. And that is an example that is kind of routinely used when it comes to explaining capsule networks, because a typical convolutional neural network cannot really you know, differentiate between a real phase, how, you know, our anatomy is, or versus a fake phase, as you will see the one on the right hand side, just as because the convolutional neural network usually it looks for information within images, right? So we have to have, you know, two eyes, one mouth, and one nose to be a face. But the capsule networks put this special component into the learning phase, so that we say, you know what, for a face to be a face, the specific landmarks in our face have to be in a specific position. So that constitutes a face, right? Otherwise, it's not. So that is one example where convolutional neural networks fail compared to capsule neural networks. Okay, so that was a bit more kind of brief introduction to deep learning. Maybe you have some questions about that. If you want to stop me now to ask, feel free. I don't mind. Or otherwise, if you prefer, we can discuss that in more details at the end of the presentation. So now, as we move on to the medical imaging example, so I thought that it would be nice when we speak about machine learning and deep learning to give an example of a non-deep learning approach when it comes to using medical imaging processes, which is the first example here with retinal images. And then I have an example which is not from my research, but is a very popular network used in medical image segmentation, which is called UNET. And then as a third one, maybe it's a bit more, I don't know, popular nowadays. I can just talk about a project that we did with an MSc in AI student for detecting COVID-19 from chest X-ray images. So that is the first example. So I think this example is a very good, opportunity to just explain the difference between, let's say, handcrafting features and automating the feature extraction, right? So what you see here is a process where we try. So what is the purpose of that pipeline is to try to detect different stages of diabetic retinopathy. So for those that are not very familiar with diabetic retinopathy, is a disease that affects the retina of the eye. Usually people with diabetes, after several years, they develop diabetic retinopathy. And the UK has diabetic retinopathy screening service where people with diabetes are screened every year or every other year to make sure that the retina doesn't have lesions, or if it has lesions, it's kept with, there's a kind of a process whereby if they deteriorate, so you have proliferative diabetic retinopathy is controlled, or you have some laser to kind of stop the progression. So the purpose of this study was to extract information from the retinal images so that then we can use this extracted information to create an intelligent system, so a machine learning system that you can detect the different stages of the disease. So in this case, personally myself, I led this study. I had to go and for instance, extract information from the retinal vessels. We have to measure, let's say, the widths of the retinal vessel. We had to identify different bifurcations that you have in the veins and arteries, as can be seen from retinal images. And of course, because we had patients that we were monitoring at different intervals, let's say year 1, year 2, year 3, then we wanted as well to automatically match the different landmarks of the retina, because as you can imagine, different capture protocols might mean that the images are not aligned perfectly. And then when you want to have an automated system that can register the different landmarks within the retinal image, then you need an algorithm that can kind of align all of the images from the same patient so that you can identify automatically, let's say, the bifurcation or junctions within the retinal vasculature, right? And of course, another step in this process is with segmentation, right? So the image that you see, the colorful image, means nothing for any algorithm. So somehow you have to identify the vessels. So that is a process where you have to find, let's say, you have to handcraft some key points, so some landmarks in the retinal image that can be used for identifying the vasculature, right? And of course, when you have all of this information, then you go on to extract all of these features that can correspond, for instance, to vein width or artery width or the length of vessels or the number of bifurcations. It could even be the, let's say, the diameter of the optic disc. So all of this information before the deep learning era had to happen manually, in a sense. So we had to handcraft these features, right? We couldn't rely on an automated feature extraction process to extract these features for us. So we had to do that as part of our developments, right? And then when you have a collection of different features, then you go on to developing different techniques that can, learn from these features. In this case, we could kind of have 4 different classes that correspond to 4 different stages of diabetic retinopathy, and then you can say, these features that you have collected, we can use them for differentiating between the different stages of diabetic retinopathy, with different levels of success, of course, right? So nothing is guaranteed, but at least you can, achieve a very good performance. So in this example and in this study, we had a very good performance with, 95–96% of accuracy on detecting the different stages of diabetic retinopathy. Of course, in diabetic retinopathy, you have lesions as well, which means that you might have, for instance, to detect macroaneurysms or hemorrhages in the retinal vasculature. But in this case, we didn't focus on the lesions because our study started at an earlier stage. So we investigated patients that are at the late stages of pre-diabetic process. So because we had a kind of a retrospective cohort, we knew when they were first diagnosed with diabetic retinopathy. And then we went back and investigated the few years before diabetic retinopathy and a couple of years after diabetic retinopathy, so that we could potentially identify the progression before lesions have appeared in the retinal vasculature, right? So this is an example of a manual process of extracting features, and that is quite demanding process. And that, if you extrapolate that, that has been happening in every medical imaging modality in the pre-deep learning era. So that means that even if you had MRI images or CT images or PET CT or PET MRI images or whatever modality, OCT, optical coherence tomography, you still had to use some sort of more established or more traditional image processing approaches that you can extract information from the image that then you can use as an input to any intelligent system, right? However, so as we move from the pre-deep learning era to the deep learning era, one of the main, let's say, problems that people have been focusing a lot on the medical imaging domain since ever has been the segmentation. So we have to differentiate segmentation from detection, because you can still detect, especially with deep learning approaches, you can still detect a disease without having to segment any lesions in the image. And that we will see in the case of the COVID-19 in our last case study. So in this example that you see here, this is one of the, if not the most established and the most successful deep learning model for image segmentation. So that was initially published 5 years ago, and since then it has attracted about 18,000 citations. So you can understand how widespread adoption this model has had. Of course, in this case, you see, if you go to figure 1, you see the architecture of the model. Of course, we're not here to speak about, the specific aspects of architectural designs, because that is a bit more technical, the discussion. But as we go on to figure 2 and figure 3 and figure 4, then you will see the results and the case studies that they use to demonstrate the performance of this approach. So in the figure 2, as part of this algorithm, what they did was that they have developed, as part of this segmentation algorithm, a subcomponent that when you want to focus on a sub, let's say on a sub part of the image, then you first identify this area, which, if you see in the example in figure 2, in the picture on the right hand side, you will see this blue box where it focuses on a specific part of the image. So they first identify where the yellow box needs to kind of be, because that is the part where we want to segment, right? So this is the part that we want to focus on. And then they first identify where the broader area around this yellow box is, and then they go on to actually focus on the yellow box itself. And that happens for what we discussed previously, so that it can reduce the computational demands when it comes to segmenting images, because there are many landmarks and many lesions potentially in the image. So to make it a bit more computationally tractable as a problem, then they first detect the sub area in the image that is of interest, and then they go on to do the segmentation, which is the yellow box there, right? So then as we move on the figure 3, again, you see a case study here, which was, for segmenting HeLa cells. And then you can see that in the image A, so in the first image, you see the raw data, what is the input data that you take directly from the capturing device. And then you see the different stages of the segmentation. So first, you have, the ground truth, because at this point you have to tell, to the model, what is the ground truth? I mean, what is the gold standard approach? So if you have an expert and they were to kind of do the segmentation manually, what would be the ideal outcome? Because that is what the model has to use to learn what is the correct way of doing that. And then you have a mask, which you can see in the image C, which is kind of a mask that shows different areas that have to be segmented. And then you go on to image D, where you see actually the first part of the algorithm, where you have the borders, so they have the margins of the different parts of the image that you want to segment. And actually, in image segmentation, and that's not only for medical images, but for every type of data, let's say image data modality, one of the most challenging problems for the segmentation is to identify this borderline picture. So for instance, if you have a tumor, like a cancerous tumor, one of the main problems is to find where the tumor finishes, where is the end of the tumor, and when the healthy, let's say, tissue starts. So that is one of the main problems, and that is maybe the most important factor when it comes to segmenting medical images, because that is where you don't want to make mistakes. So that's where you want to minimize any mistakes. And of course, other models that have been developed in the past, like active contour models, you try kind of to approximate this border. So you go slowly as you expand your segmentation area to kind of slowly go pixel by pixel and then identify, where you have to stop, right? But you have to consider that in all of these, processes, if you want to create something that's robust and properly validated, you have to have a proper ground truth that you can kind of benchmark your algorithms against, right? Otherwise, you won't be able to understand how successful your approach is, right? And of course, on the figure, in figure 4, they show example, another type of cell tracking image. And that is, I think, a challenge. So that is kind of similar to Kaggle competition, if you say like that. But ISBI is one of the biomedical informatics conferences where they have some challenges sometimes for people participating in the conference if they want to benchmark their techniques against specific data sets, right? So you see similar, results based on what you have seen as well in figure 3, but for different type of images, right? So then, as we move to our last case study, that is the COVID-19 detection from X-ray images. That was a project that we did over the summer with an MSc student here. Of course, there's only so much you can do in 3 months when it comes to developing something involving medical imaging. But we tried to do something different to what other researchers have done. So one of the main problems that we identified early on in the detection of COVID-19 from X-ray images is the fact that the data sets that were made available to the community, usually they were coming from, let's say, different hospitals. And then when you aggregate data from different sources, then you risk to kind of, especially when you have very small data sets, right? You risk to have huge variability in the capturing process. And then when you develop a system, you have to be very careful when you try to detect, let's say, COVID-19 versus, let's say, healthy subjects, because sometimes it might be that the COVID-19 examples come from a specific hospital, whereas the normal X-rays come from another hospital. So the capturing protocols might be different. So when you develop a system to detect COVID-19 from different data sets, it might be that the model that you develop actually detects not the anatomical differences that you might have because of the disease, but because of the image properties that you might have, right? So there were some early results in COVID-19 where researchers kind of documented some inflated performances for detecting COVID-19 from X-ray images. And then there was another paper that was published, I think around May, that then they said, what you have been developing so far might not be as robust and reliable as you might have thought, because if you don't follow a proper protocol for evaluation, then you might, end up having, performances that do not correspond to reality. So what they did, they proposed, and basically they did an experiment, which you can see in the figure at the bottom, where they removed the main part of the chest, and then they say, okay, let's see if we can detect now COVID-19 from images that have this black box in the middle of the image. And then they found that many of the proposed approaches, they could actually detect COVID-19 from images like that. So I hope you can understand that, there is no COVID-19 present in any of these images because it's removed, that part of the image. So what was happening is that they were detecting, COVID-19 just because the different images were coming from different hospitals. So that was the information that the model was using to differentiate between the different imaging, different medical images for the disease or no disease in this case, right? So what we did was actually to use less complex models, right? So because one of the main problems that usually lead to such issues is when you have, let's say, very complex models that they are overfitted, so they don't generalize well. So then you have new images, they don't perform as well as they would in cases where we had an abundance of data, right? So then we took a different approach. So we thought that, given that we have very few images, let's focus on developing some simpler models, some simpler deep learning models, and use only medical images to train them. Because if you have read some papers on COVID-19 with deep learning, you will see that sometimes people are using models that have been trained with other images as well. So they have been trained with natural images, like natural scenes for object detection. And there is a good reason why that happens. And the reason is that, there are some information that you can still learn from generic images that can be useful for medical images, because, you might have, specific structures, let's say, lines and edges and shapes that you find in objects as well as, in medical images. But sometimes when the problem that we're trying to solve is very specialized, then sometimes we might have only to use images that correspond to this problem that we're trying to tackle. So then we took that line of approach, and then we developed a system that we can detect, COVID-19 versus bacterial pneumonia, and then normal cases. And then we got some good results, but bear with me that, our main objective was not to kind of beat the state of the art to create something that's robust necessarily, but the point was to kind of create something that is a student project. But nevertheless, the results that we obtained were very good, and we decided to kind of submit a journal paper, and it was kind of, we had the first round of reviews, and now it's under revision. So what you see in the first figure on top, you'll see a blue arrow pointing to some images that's called class activation mapping heat map. So this is let's say, a system that you can embed in your medical imaging pipeline, that it can give you some indications through a heat map, right, on which areas within the image were the most important ones for predicting the specific outcome. For instance, if it gives you that this specific image is a COVID-19 image, then it will show you with a heat map which area within the chest, within the anatomy of the person the chest part of the person, which part of the chest shows COVID-19 symptoms, and that is the part of the image that the model considered to be the most important one for differentiating between COVID-19 versus other types of inputs. In this case, we had, let's say, 3 different categories: one for bacterial pneumonia, one for COVID-19, and one for normal. So we incorporated that extra step, which maybe it's something towards more the let's say, transparency, if you want to call it like that, or interpretability, but something extra so that it shows you an indication on what areas of the image might be the most important ones for the different categories. Of course, bear with me again, when I explain that, these approaches are not robust in terms of, showing only the areas that are actually true, right? Otherwise, we would have solved the problem of interpretability in deep learning, and that's not the case. But that is an extra step that potentially can give you some visual information about what areas in the image might be more important for the prediction that you are getting out of this intelligent system, right? So that is what we did in a nutshell. So that is the last case study. So I guess when we speak about medical imaging, and based on my experience, as I said before, I used to work in medical imaging. I am not working really anymore in medical imaging. The reason is, to some extent, of course, it hasn't happened, if I can say it like that. Another reason is sometimes, data availability is a problem in medical imaging. And of course, it depends on who you are collaborating with, right? So if you don't have enough data available, then it's very hard to conceptualize some novel approaches to solve a problem. So, and if you consider ethical, approvals that you might have to consider, then some projects stretch, for a much longer period of time, without being able to actually do some novel development. So these are things that we have to consider when it comes to medical imaging, so availability of data just to start with. Of course, when we have much data, and that is an ideal scenario, then you have to start thinking about scalability. So, and when it comes to scalability, means that we have to create bigger models, more complex models, and that leads to more computational demanding approaches, right? Of course, then we go on to more other type of problems that I don't think they are specific on the medical imaging. They are, in other application areas where you have to create an understanding between different, people involved in the project, like clinicians or medical practitioners, radiologists or computer scientists, engineers. So you have to find, a line of communication, understand what are the expectations from each of these groups. So that is, one of the open problems when it comes to establishing long-term collaborations in medical imaging. Of course, very popular one that I guess it is quite, even more popular recently is, how transparent these approaches are. I mean, can you explain why your decision was X and not Y? Can you provide, robust explanations that, the clinicians can use, as part of their, decision-making process? But of course, that comes sometimes at a trade-off. So we have to think that there is no such thing as a free lunch. So sometimes the way that we are now, we have to consider, if the objective, and that of course depends on the problem that we're trying to solve, if the objective is to get high performance or to be more transparent. And of course, there is a whole body of research happening at the moment where they try to find, a way of incorporating even more transparent approaches into the deep learning pipeline, so that you have an algorithm that can, be more transparent and at the same time be quite accurate in the performance. Of course, technical challenges is always a problem because sometimes we think about the application, but then we have to consider that different type of data might require some theoretical research alongside, and that might take time. So it's not only applying established techniques, but sometimes when we want to push the boundaries of performance, we might have to consider, some ideas on how to improve the theoretical aspects of the techniques involved, right? And of course, I believe, and I have seen that in the past happening, that sometimes, of course, you have many, big universities that are doing research on medical imaging. You might have, I don't know, could be Aberdeen, it could be, UCL, King's College, Imperial or Manchester. They have, very big medical imaging teams. And they also have, huge data sets to work with, and maybe they have access to data sets that might help them to develop bespoke algorithms that others cannot do because they don't have this type of data. And that happens, in any type of setting.